welcome to lecture number 45, and we have been discussing about how to solve system equation or rather differential equations when the excitation is any function x t using Laplace transformation. So, in our last class I introduced with the concept of Laplace transform and Laplace transform of various useful functions. Okay. Today, we will continue with that. For example, we will try to find out, for example, we have seen that Laplace transform of u t is equal to, I mean some results I am just writing 1 by s. We have seen, similarly, we have seen that Laplace transform of e to the power a t into x into u t, this is 1 by s minus a, is not, that is what we have seen. So, we are discussing with unilateral Laplace transform, that is from 0 to infinity, we will integrate the function, and the basic definition of Laplace transform of x t as we have seen is equal to this integral 0 to infinity e to the power minus s t into x t dt, and this is we were writing as, because it will be a function of s, where s is a complex number sigma plus j omega. So, this is putting these values, integrating it, we got some results of Laplace transform of some useful functions. First, let us today do another Laplace transform of another function, which is delta t, unit impulse function, which is just very simple, but only thing is this delta t function exists from 0 minus, exists between 0 minus to 0 plus. So, this integration I will then carry out from 0 minus to 0 plus, because 0 to infinity, instead of that it is like this, and then e to the power minus s t into delta t dt. Because beyond 0 plus the value of the delta t is 0. So, this integral 0 to infinity is essentially 0 minus to 0 plus, but when you integrate it this function, it is a function multiplied by delta t. So, so this will be actually the functional value of this at t equal to 0, that is this will be equal to then 1. Therefore, mind you that Laplace transform of delta t is equal to 1. This is another useful results. Apart from that, we have found out the Laplace transform of differential of a function, integral of a function, and so on. Now, today we would like to know what will be the Laplace transform of say sin omega t. What is the Laplace transform of this, and what is the Laplace transform of cosine omega t? Of course, sin omega t into u t, mind you, that is important, into u t. Now, these things can be derived very easily, and I will take recourse of this particular formula, that is Laplace transform of e to the power a t u t is equal to 1 by s minus a, where a could be also imaginary, it does not matter, a is a some constant number. Therefore, what you do is this, we will first try to find out Laplace transform of This is the easiest way to find out the Laplace transform of e to the power j omega t. So, using that result, I can say that where j omega is the imaginary constant number and this is t. Therefore, by virtue of this formula, we will say that it is equal to 1 over s minus a, is not s minus j omega, it will be, because the value of a is j omega in this particular case. Now, or this Laplace transform of e to the power j omega t into u t, of course, is nothing but Laplace transform of cosine omega t plus j of cosine omega t u t plus j of sine omega t into u t, is not? And this Laplace transform is 1 over s minus j omega. Now, this thing I can multiply with s plus j omega, both numerator and denominator, and if you do that, then you will get here omega square. Mind you, j is root over minus 1. So, this can be written as s by square plus omega square plus j omega by square plus omega square. So, Laplace transform of cos omega t u t plus Laplace transform. So, this can be written as Laplace transform of cos omega t u t plus j Laplace transform of sin omega t into u t. And this we have got this to be equal to s square plus omega square plus j omega by s square plus omega square. Therefore, the real parts and real parts will be same, and imaginary parts, if you equate, you will get the same results. Therefore, equating the real parts, I will say Laplace transform of cosine omega t into u t is nothing but s by s square plus omega square and Laplace transform of sin omega t u t is nothing but omega by s square plus omega square. So, these two results are very useful in circuit analysis, because our inputs may be sinusoidal functions, which is quite common, and so these two results are very important. So, easier way to remember it, cos omega t. So, cos, that s is in the numerator, denominator is s square plus omega square in both cos and sin Laplace transform, and for sin omega t on the numerator it will be omega by s square plus omega square, that I must remember correctly. Okay. Therefore, these are the Laplace transform of these two important sinusoidal functions, sine and cos. Okay. Now, for example, if I say, let us try to now write down some asking you something. For example, if I say Laplace transform of e to the power a t into sin omega t, what will be its Laplace transform? we know, we will write like this, argue like this, we know Laplace transform, I mean into ut, of course. We know Laplace transform of sin omega t ut is equal to omega by a square plus omega square. If this is true, then Laplace transform of e to the power a t sin omega t ut, it will be same thing, but s is replaced by s minus a. This is the idea. Got the point? Therefore, the earlier results that we got, if we know the Laplace transform of x t, which is capital X s s, then if you multiply that function with an exponential e to the power a t, is same Laplace transform, but s is replaced by s minus a. Similarly, for cosine omega t, Laplace transform of e to the power a t cosine omega t into u t. For cosine omega t, Laplace transform is s by s square plus omega square, that is what we have seen. But since it is multiplied by e to the power a t, s should be replaced by s minus a. Wherever s occurs on the right hand side should be replaced by s minus a, like that. Now, what is the idea? Idea is, I will take the Laplace transform of a given differential equations and it will result into an algebraic equations, and then whatever output I am interested in, I will take the Laplace inverse of that. So, mind you, x t and x s form a pair. If you know x t, then x s we have written several times, it is equal to 0 to infinity for one sided Laplace transform e to the power minus s t into x t into d t. Is not? That is what we have been writing. What is the inverse relationship? That is, if I know x s, what should be x t? I will simply write down without proving anything that x t inverse Laplace transform that is Laplace inverse of x s is equal to x t. It will give you x t. Now, what is this operation Laplace inverse? It will be shown, it can be shown that x t is equal to 1 over 2 pi j, then sigma minus infinity to sigma plus j infinity into x s into e to the power s t d s. So, if you integrate this function, which looks very much complex, and but anyway it can be done and you can get the corresponding time domain description of x s. Then it looks like it may be a very difficult task when I want to apply this to find out the response of some circuit in time domain. I go to Laplace domain, no doubt, but then I have to come back to time domain taking the inverse. But the easiest way to do it, we will not use this. This equation will not be necessary to get Laplace inverse. In fact, we will try to avoid the use of this rather complex looking equations. To xs is known, multiply with e to the power s t, integrate it, get the time domain description. Instead, what people do is this: for some standard function x t and x s, for example, I will better write it in this way. For example, we have seen that Laplace transform of say unit step is equal to 1 over s. Then I will say this table I have to remember, this is I have evaluated, this I have already evaluated. So, I will say Laplace inverse of 1 by s is equal to unit step. So, look at the description on the right hand side, try to fit it with some transformed formula, then you are done. For example, Laplace transform of e to the power 5 t into u t is equal to 1 over s minus 5, correct. Therefore, I will say that Laplace inverse of 1 by s minus 5 is nothing but e to the power 5 t into u t, like that. Got the point. Similarly, Laplace inverse of this function, for example, I am just writing some function Laplace inverse of 2 by s square plus 4. Suppose I have been asked to find out what is the Laplace inverse of this. This s square plus 4 means Laplace inverse of 2 by s square plus 2 square, is not? Now, I know Laplace transform of cosine omega t or sin omega t is equal to omega by s square plus omega square. Therefore, you just match these two and say that the Laplace inverse of this quantity is nothing but sin 2 t into u t, that is all. Got the point. Similarly, suppose somebody says Laplace inverse of 1 by s square plus 9. What I am going to do is this, I will say that Laplace inverse of 1 by s square plus 3 square. But you see there is no 3 here. So, what you have to do is this, you have to multiply with a constant 1/3 and say that Laplace inverse of 3 by s square plus 3 square. That is what you do, what I am doing here, I must bring this 3 here on the top, and so I will say okay, multiply with 3 and divide with 3 in the numerator. Then I will say this is the Laplace transform of 1/3 sin 3 t into u t. Got the point. So, I have to looking at this standard transformed formula or looking at some Laplace transform table, I should cast my Laplace transform equation in such a fashion that its inverse can be readily understood by me, and that way we will be applying this formula to take the inverse. So, while taking the inverse, we are not going to use this so called complex equation. Then the all the advantages goes every time you take the inverse of this complex equation. So, beforehand we make some table and our input signals after knowing several properties of Laplace transform can be easily found out. So, so this is the scenario. There are other properties of Laplace transform, very interesting properties, but since our focus will be how to apply this in network analysis, I will just take a simple example and try to first tell you what it is all about. Okay. Now, let us come to an example. For example, the standard problem that we have already done, suppose you have an R and an inductor L, and here you apply a voltage which is suppose ut, unit step voltage. What is the nature of the voltage? Nature of the voltage, as you know, it was 0 all along up to t equal to 0, then there is a step jump of 1. So, you are applying a DC voltage across the network from t equal to 0, is not? This is ut and this happens to be your excitation x t. I want to find out what will be the current in this circuit. Now, try to follow me very carefully. So, I want to sketch I t. This result is already known by classical method, but let us try to apply the rule in the Laplace transform domain. Okay. So, what I am going to do is this, I will write down first the differential equation, and this we know L d I dt, and this we know R I with the assumed direction of the current. Then I will say the equation is L d I dt plus R I is equal to u t. So, in the time domain the differential equation is like this. Then you can take Laplace transform of both the sides. Take these points, you just try to note, take Laplace transform of both the sides. If you take Laplace transform of both the sides, you will get Laplace transform of L d I dt, L can be taken outside, L being a constant, Laplace transform of d I dt plus R Laplace transform of this variable, time domain variable I, which is still not known, and on the right hand side I will get Laplace transform of unit step u t. Now, let Laplace transform of I t, which is the unknown which I want to find out, be denoted by this capital letter I s. So, this one L into what will be there? Laplace transform, it is S I s minus I 0 minus. You recall the differentiation formula of a time domain function, its Laplace transform is S I s minus I 0 minus 1 plus R into Laplace transform of this one is I s, and this is equal to 1 by s, and we want to get solution for t greater than 0. So, these I s are whatever time function you will get there for t greater than 0. So, this is the thing, or I can say that S L plus this term and this term you group together, minus L I 0 minus is equal to 1 over S here. This will be the thing into I s. Suppose I 0 minus is equal to 0, there was no initial current, then this equation would have been R plus S L into I s is equal to 1 over S, is not? So, I get an algebraic equation. So, this is an algebraic equation. Our goal is to find out I s. So, what next I will do is this, therefore, I will write I s is nothing but 1 over S was there, this thing will come down here R plus S L, is not? That will be the thing. Then of course, my goal is to find out I t. What is I t? That is my final goal. In real time, what will be the value of the current when such a voltage has been applied across an series RL combination. Next step will be therefore, I t. What you have to do is you have to take Laplace inverse of I s, and if you take Laplace inverse you will get the I t. Now, let us do this. So, I have got now I s, I have got it to be how much here S into R plus S L. So, right here S into this is S plus R plus S L. Is not? This is the thing, and by 1. Now, this thing, see, in Laplace transform the formulas we know is S plus something, not 2S. So, this L you take common. So, I will take common of L. So, 1 by L you take common, and then it will look like 1 by S plus R by L into S, is not? This will be the thing. Now, what you have to do is this, you have to take does it fit into any of the known formulas? Really not so, right now I am not sure. So, what I will be doing is you break it up into some partial fraction, try to write it in this form, A by S plus some B by S plus R by L, and try to find out the constants A and B. In this case, it is so simple, that is why I will not I can do mentally. So, also you. What you do is this, on the top it is S into S plus R by L, it is there. So, on the top there is a constant, what you do, you add this, then minus S, there is no S terms. So, you do it like this, and then there is no R by L also on the top. So, multiply this thing with L by R, got the point. So, this and this are one and the same. If you just manipulate this, S S goes, R by L multiplied with L by R will give rise to 0 here, got the point. Therefore, this will simply become equal to 1 by r into this thing. So, you separate these two terms. So, it will become 1 by s minus s goes and it will be s plus r by L. Got the point. So, I s will be equal to 1 over r into 1 over s minus 1 over r into 1 over s plus r by L. Isn't it? This is the thing. Now, you look at these things. I t is equal to Laplace inverse of I s, which means 1 by r. I am writing elaborately, so that you do not miss these steps. Later it will not be necessary when you become habituated with it. So, Laplace inverse of this minus 1 by r Laplace inverse of 1 by s plus r by L. This is 1. Now, what is the Laplace inverse of 1 by s? It is u t. So, 1 by r into u t. And what is the Laplace inverse of 1 by s plus r L? It is nothing but e to the power, this is the value of a, Laplace inverse. So, e to the power minus of r by L into t into u t, and by 1 by r. So, the result will be 1 by r into 1 minus e to the power minus r by L into t into u t, and that is equal to your I t. So, interesting point to be noted, that if you want to solve a differential equation using Laplace transform, you know that it will give you the complete solution in one stroke, including even if there is some initial condition. Here of course, I have taken I 0 minus is equal to 0, you could also carry on with this I 0 minus, no problem. And take the Laplace transform, write down the differential equation, take Laplace transform of both the sides, and I will write down differential equation only. So, this formula is to be remembered, Laplace transform of dx dt is a s into x s minus I x 0. So, using that formula, only thing here instead of x it is the I you take, and Laplace transform of the input signal must be known, a known signal. So, 1 by s, and then manipulate these terms, this is algebraic equation. So, as if you are solving a DC circuit, I s is equal to some this by this. Therefore, finally, you arrange this term appropriately, so that you can connect, you can easily make up your mind that what will be the Laplace inverse of 1 by s. In that form, you have to break these two terms. By partial fraction, you can also do it, but it is so simple a case, I did it, just mentally you can also do it. So, do it like this, then take Laplace inverse. Laplace inverse of 1 by s is a standard thing, unit step. Laplace inverse by of s plus 1 by s plus r by L is also standard, e to the power minus a t u t. So, what are the formulas we have used? Here I have used two things, two results, Laplace inverse of u t is 1 by s and Laplace inverse of e to the power minus a t into u t is equal to 1 by s plus a. I think you have got the idea. We will talk on this in the next class. Thank you.